Right. Next, in example 2, we're going to try and use that same strategy of getting a common log and being able to ignore it. But you'll notice here that I've got a log on the left-hand side with an x in it, but I've got just a number 1 on the right-hand side. So I would like to somehow change this 1 into some sort of logarithm so that I can have a common log and ignore it. So I'm going to give you a second and talk to your elbow partner and see if you can think of a way to change 1 into a logarithm. There's lots of logarithms that equal 1. See if you can talk and figure out which one might be helpful here. Okay, if you need more time, feel free to pause, but I'm going to start talking about it. I'm going to do it off to the side, so I'm going to call this on the side. So this doesn't have anything to do with this question, but I just want us to talk about it. I want you to consider this. I want you to consider log 3 base 3. What does that mean? That means what exponent do you put on 3 to get 3? Well, I'm pretty sure the answer is 1. So 1 can be expressed as log 3 base 3. Another way you could express log, or 1, would be like log 17 base 17. Again, what exponent do you put on 17 to get 17? Well, 17 to the power of 1. So you can express 1 as all sorts of different ones. In this particular case, do you think we're going to use log 17 base 17? Probably not. Log 3 base 3? Probably not. What we're going to want to do is find the one with the same log as over here. So instead, I'm going to change this 1 into log 5 base 5. Okay? So 1 is log 5 base 5. Because that asks what exponent do I put on a 5 to get a 5? It's 5 to the power of 1. Over here, this is all the same. So this is based on this idea right here. Maybe you came up with it on your own. Maybe you're seeing it now. But I want you to be aware of it. Just to extend this idea, what if I wanted to do 2? There's 2 ways we could think of 2. We could think of it as 1 plus 1 and convert it twice and say, okay, let's do base 5 again. So this 2, or this 1 can change to log 5 base 5. And this one can change log 5 base 5. And since they are the same, you've got log 5 base 5 and log 5 base 5. You've got 2 of them, so 2 log 5 base 5. Where can that 2 go? That 2 can come up the exponent and say log 5 squared base 5. So 2 can be expressed as log 5 base 5, or 5 squared base 5. And that makes sense because remember, this is asking what exponent do you put on 5 to get 5 squared? Well, a 2. So another way you could express 2 in a different example, 2 could be log 3 squared, or 9. Okay, so there's lots of ways you can do this. If I ask for base, like 4, or sorry, I had a 4, and I want to change it to a logarithm. Let's just pick anything to log 7. Give me 7 to the power 4, because it's what exponent do you put on 7 to get 7 to the power 4? Well, it's 4. Okay, so that's just all on the side. Why is that important for this question? Well, it allowed us to change this number into a logarithm. Why is that important? Well, we just discovered in example 1, once we have a common log, we can ignore the logs and look simply at the answers. So again, the therefore is really important. Equals 5. And now I can solve for 3. The 3 will come over here, 5 plus 3, and x equals 8. So the trick in this one, or the new thing on there, is being able to convert a number into a logarithm. I'm just going to double check that this answer is correct. So I'm just going to check this. So does 8 work? Well, if I put 8 back into the equation, it would be log 8 minus 3. So that would be log, base 5. 5, and then it would be asking what exponent do I put on 5 to get a 5? Is 1, so it works. It verifies. I'm sure some of you are asking, do I need to do that verification all the time? And you're going to see an answer to that question very, very quickly. So this one may be a bit of an overkill to check. We'll see if it's always going to be important, then we'll make a rule in a moment. So let's see if we can apply this in a different question. So in B, we've got log of x plus 2, and then log of x minus 1, and it equals 1. So the first thing you're going to notice is we're dealing with log. It just says log. What's the exponent, or sorry, the base when we just see log? Well, that's understood that it is the common log and base 10, right? So remember, this is like a little base 10 here, a base 10 here, even though it's not written. So first things first, I have this 1 at the end. So again, I'd like to convert it to a logarithm. This time I'm going to do it with log base 10. So based on what we just did on the aside, this can convert to log 10 base 10. And on the left-hand side, you see I've got a term with an x on it here, and a term with an x on it here. The good news is they have the same logs, and I'm adding them. So I can bring them into a single log through multiplication. So I can bring it to log base 10. I don't need this little 10 there, but I'm going to do it anyways. And I can multiply the answers. So this would be x plus 2 times x minus 1. So what you're going to notice now is I've got common log on this side, common log on this side. I can ignore them. So therefore, x plus 2 times x minus 1 equals 10. I have to solve for x. Well, I'm going to have to do some rainbow, and this part I'll do relatively quickly because it's the easy grade 10 math here. So x times x is x squared minus x, 1x, plus 2x minus 2 equals 10. I notice it's a quadratic, which means a strategy when solving quadratics is to have everything on one side and have it equal to 0. In the other ones, there might have been linear, so I had a different strategy. But this one is quadratic, so I'm going to have x squared. Bring everything to one side and collect like terms, get a plus 1x. Bring this across, and it becomes a minus 10. Plus the minus 2 is minus 12. Quadratics also tell me to factor. So I need two numbers to multiply to negative 12 and add to negative 1. Or sorry, positive 1. This can be a plus 4 and a minus 3. And therefore, then I'll get two answers of negative 4 and 3. So it turns out this one has two possible answers. So the logarithm part is really just happening in the first line, using the product rule to bring things together into a single base, and using the idea of converting a number into a logarithm. After that, since they have common logs, it's just a simple quadratic solve. Bring back this idea of verify. So we should double check that each of these work. So we'll start by double checking negative 4. So I'm going to take negative 4 and sub it into the logarithms. So it'll be log, used to be x plus 2, but now it's negative 4 plus 2. Now I know there's more to it, but I already see a problem. This is going off and it's going to say log negative 2. So this is saying what exponent do you put on 10 to get a negative number, a negative 2? And that's impossible. If we think back to our earlier properties of logarithms, it's impossible to take the log of negative numbers, at least in what we're studying. You can do it later on, but right now we can't. Because it's saying, what exponent do I put on a positive base to get a negative number? That's impossible. If you put in positive exponents, it'll get big. If you put in negative exponents are fractions. So there is no exponent that you can put on a positive base that gets you a negative number. So what does that mean? That means that this negative 4 is not going to work. Does not verify. It wouldn't have worked in the other half too, about log negative 4 minus 1, but all I had to do was see it fail in one spot. I am going to check though the 3. Will 3 work okay? Yeah. And I don't have to necessarily write this down. I just got to do a check, so it'll be 3 plus 2, which would be a log 5. That's okay. And the minus 1 here is still okay, so it's log 3 minus 1, which is log 2, and that's okay. So that means that this is the only one that verifies. Therefore, you only have one answer. So if we go back to the last question and say, should I verify all the time? The answer is yes. You cannot be taking the log of negative numbers. So you got to make sure that your value for x that you solve does not result in you taking a log of a negative number. In this case, negative 4 would have resulted in a negative, taking the log of a negative number, but 3 is okay. And so there's only one answer. All right, we'll do one more example like this. Again, this is just bringing the idea of converting a number into a logarithm. So this time we got to deal with this 4. Let's go back to the aside. There's a bunch of ways you can do this. Let's go back actually. There's the aside. So here was an example where we had 4. 4 can be converted, if I was using base 7, as 7 to the power of 4, base 7. 2 converted to 3 squared, base 3. Or 2 could be 5 squared, base 5. So if we go back to this example that we're dealing with, this is 4, and the base that I want is 2. So this would be log 2 to the 4, base 2. Because remember, it explains, this is asking what exponent do I put on 2 to get 2 to the power of 4 is 4. That's what I want. You could also consider a 4 to be 1 plus 1 plus 1 plus 1 and do a whole bunch of log 2 base 2. This one changes to log 2 base 2. This one changes to 2 base 2, 2 base 2, 2 base 2. You'd have a total of 4 of them. So it would be 4 log 2 base 2. And that 4 can come up top to 2 to the power of 4. So both of those are long-winded explanations to say that in this one I can change this. Oops. Base 2. Into that. And the left-hand side would change, or stay, 3x minus 5. Of course, the reason I chose base 2 in this particular example is so that I could have a common log of base 2, so that I might be able to ignore them. So 3x minus 5 equals 2 to the power 4. 3x minus 5 equals 2 to the power 4 is 2 times 2 times 2 times 2, which is 16. So 3x equals 21, x equals 7. I should just verify. And it'll be log 2 would be 3 times 7 minus 5. That's going to be positive, right? It'll be 21 minus 5, so it's log 2 of 16, which is 4, so it works. I really didn't necessarily need to show that it's 4. I just needed to care. I cared that this was a positive number. Or better yet, this 7 didn't produce the log of a negative, which is not allowed.